Hello everyone and welcome to this new problem. In this case we are trying to solve a non-homogeneous ordinary differential equation, but first we are required to verify, and that's always nice since it doesn't say solve, so please don't solve at the beginning, just verify. What do we have to verify? Well, here we have a second order due to the second derivative, linear. It's a linear combination of the output x and some of its derivatives. Non-homogeneous ordinary differential equation due to the t cubed term on the right with variable coefficients. In other words, everything is changing here, everything is varying, and that's always a bit of a nightmare, but we'll survive. So we need to verify x equals t as one of the homogeneous solutions. So assuming 0 on the right of the differential equation, we need to verify that x equals t verifies that homogeneous. So if x equals t, second order means we need to reach the second derivative, x prime equals 1, x double prime equals 0, substitute in the associated homogeneous. So t squared times x double prime times 0 minus t times t plus 2 x prime, which is 1, plus t plus 2 times x, which is t, equals 0. We are verifying the associated homogeneous. Now the first term goes to 0, and we have the same term in brackets, t plus 2, both multiplied by t with opposite signs, and therefore they cancel out. Hence we verify x equals t as one of the homogeneous solutions. So x homogeneous as a function of t equals constant times t plus constant times something else, and therefore we must find that second contribution to the homogeneous solution. So we know that when everything is changing, when the coefficients are variable, x homogeneous equals a mysterious function u times x homogeneous particular. So more specifically, u times t. And our goal is to find that mysterious function u. Again, second derivative, so first derivative, x prime. I'm gonna drop the subscripts so that it looks better, less confusing. Derivative of the first, u prime, times the second, plus the first times derivative of the second. Derivative of t, 1. The input variable is t. We are differentiating with respect to t. Second derivative, product rule, derivative of the first, u double prime, times the second, plus the first times derivative of the second, again 1, plus derivative of u, u prime. So this is u double prime t plus 2 times u prime. Substitute in the homogeneous differential equation. So t squared times x double prime, u double prime t plus 2u prime minus t times t plus 2 times x prime, which is u prime t plus u, plus t plus 2 times x ut. Is this equal to 0? Multiply everywhere, u double prime times t cubed plus 2u prime t squared minus, I'm going to multiply first here this term, so it's t squared plus 2t, keep the minus in front, times u prime t plus u, and then plus ut squared plus 2ut equals 0. Getting closer, u double prime t cubed plus 2u prime t squared, and then again unfold, multiply, minus u prime t cubed, first times second, minus ut squared, second times first, minus u prime 2u prime, t squared, and then minus 2ut. plus ut squared plus 2ut equals 0. Here we have a nice checkpoint. We know for sure that at the very least all the u terms must be gone, must cancel out. So 2ut minus 2ut cancel out. Ut squared minus ut squared, and oh, so lucky, 2u prime t squared minus 2u prime t squared. So all of a sudden everything gets simplified to u double prime t cubed minus u prime t cubed equals 0. Factor out t cubed times u double prime minus u prime equals 0, and here we have two options. What if t equals 0, right? Not very interesting. We must explore that option just in case. Remember that before cancelling out a variable, in order not to lose information, we should explore the possibility of what if that variable is ever equal to 0. But checking in the original differential equation, if x equals 0, we have t squared times x double prime, so 0, and substituting in here in the main equation, minus again times t, which is 0, plus 0 plus 2 times x equals t cubed, 0. So I mean, it's just a point, x equals 0, t equals 0. Not very interesting. A constant output, null output, well, but we covered that option. So much more interesting, what if u double prime minus u prime equals 0? And even though it's a second order, given our nice checkpoint that all the u terms must be gone, that means that this second order differential equation must be reducible. Okay? So there's no output, and therefore we have a nice substitution. If u prime equals, rename it n, then u double prime equals n prime. Okay? So we obtain m prime minus m equals 0, which is first order separator. Let's solve it next slide. Okay. So we have m prime minus m equals 0, which is dn dt equals n. So dm over m equals dt, and now integrate left and right. So natural log of m on the left equals t plus constant. We already used c, so let me use a in this case. Exponentiate left and right. Okay, so e to the, and we obtain m equals e to the a constant, is another constant. Abusing of notation, I'm going to rename it as a, why not, times e to the t. But m means nothing, it was just a substitution tool, so substitute back, m was u prime. Okay, so if u prime equals a e to the t, then u, mysterious function u, is the integral of a e to the t dt, which is a e to the t plus b. So finally, our homogeneous solution, which was function u times t, is going to be a e to the t plus b times t, and that is a e to the t times t plus bt. This is the homogeneous solution. Okay, that's step one. So here we have two linearly independent contributions. This is x1 and t is x2. It appears naturally. It was part of the initial information. Remember, verify x equals t as one of the homogeneous solution. And here we have it. T is one of the independent homogeneous contributions. So for step 2, now it's time to take care of the non-homogeneous part. Take care of non-homogeneous. For that option, there's 2 paths available to us. Undetermined coefficients and variation of parameters. Since we are practicing for the exam, I'm gonna solve this problem using both methods, although obviously just pick one of them. So using undetermined coefficients. Well, based on the non-homogeneous equation that we had at the beginning, it was the ODE equals t cubed, right? And more specifically is t squared x double prime. Oh, sorry. So t squared x double prime minus t times t plus 2 x prime plus t plus 2x equals t cubed. Let's divide everywhere by 1 over t squared so that the leading coefficient is 1. Super important when solving the non-homogeneous parts. So x double prime minus t plus 2 over t x prime plus t plus 2 over t squared times x equals just t. So based on the non-homogeneous part, our guess for the particular solution is, remember the rules. Side note, I'll include the rules in the bottom right corner. When guessing our particular solution, sines and cosines always in pairs. Use all powers of x to the k, and bump if our guess overlaps with the homogeneous solution with xh. Okay, so we don't have sines or cosines, so rule 1 is useless in this case. Use all the powers, so our guess should be constant. I'm going to use t plus f, because we need to decrease the constant until we get x to the 0, input to the 0, in this case t to the 0. Okay, this is our guess. And it does not overlap with the homogeneous solution. Well, it does with the t, right? Not with e to the t times t, so x2 from the homogeneous solution was t, and our guess includes a t, so according to rule number 3, we bump until it does not overlap anymore. So this is our guess. Substitute in the differential equation. Second order, so up to the second derivative. X particular prime is 2et, and derivative of f, 0. E and f are constants. xp second derivative, 2e. Substitute in ODE, and we have substitute in ODE, so we have x double prime, which is 2e minus t plus 2 divided by t x prime, 2et plus t plus 2 divided t squared times x, e t squared plus f equals t. Okay, so far so good. Then keep going, multiply and regroup by analogous structures. So we have, well, before doing so, let's simplify a little bit. This and this cancel out. So there is 2e minus 2et minus 4e, right? Two e minus 2et minus 4e. And then once we multiply these two, well, I will write them just for the sake of the argument. So plus t plus 2 over t squared times et squared plus f equals t. So on the left, simplify 2e minus 4e, negative 2e minus 2et. And then first times the entire brackets, cancel out the t squared and t squared, so it would be plus t plus 2e. And then second times the entire brackets plus f times t plus 2 over t squared equals t. So minus 2e minus 2et plus et plus 2e plus ft once we multiply plus f over t plus 2f over t squared must be equal to t. And then group by similar structures, minus 2e plus 2e, they cancel out. On the left we have minus et, right? On the right we have just 1t, so e must be negative 1. There's no other way. Moreover, on the left we have structure 1 over t and structure 2 over t squared. None of them survive on the right, so the only way to get rid of them is when f equals 0. There's no other way. So our particular solution, which was, allow me to go back a little bit, et squared plus f, right, is just f equals 0, e equals negative 1. So our particular solution is just minus t squared. And therefore, we claim that this general solution, including both homogeneous and non-homogeneous part, x of t is the homogeneous solution plus the particular solution. So homogeneous solution, constant t e to the t plus constant t. So constant e to the t times t plus another constant times t minus t squared. That would be the solution of the entire differential equation. Okay. Now, a few minutes ago we mentioned that we were going to solve the second step, taking care of the non-homogeneous part, using both methods, undetermined coefficients and variation of parameters. So, using variation of parameters, we need the homogeneous solutions, their structure. x1 was e to the t times t, and x2 was t. So we know that the general solution x to the t equals mysterious function u1 times x1 plus mysterious function u2 times x2. More specifically, u1 times e to the t times t plus u2 times t. And the goal is to retrieve u1 and u2 to build the general solution using this method. Well, u1, according to the formulas, equals the integral of a fraction. Upstairs, we're solving for the quote-unquote first unknown, so it's like using Cramer's method when solving differential equations. In fact, we are doing just that, using Cramer's method. So 0 and non-homogeneous part, and here we have x2 prime. Downstairs, in the denominator, the Wronskian. x1, x2, x1 prime, x2 prime. Integral with respect to t. So this is the integral of. We need some additional information. So bottom right corner, some side note. This method works when having 1 as leading coefficient. Y to the n, the nth derivative, not y to the n, sorry, the nth derivative of y plus plus a given term f0 times y equals f of t of the input. And this is what we have, very common mistake, this is what we have once we divide by 1 over t squared. I'm sure if you did it at home, chances are that you took t cubed for capital F. Please don't do that, it's a frequent mistake. Don't take the right hand side of the differential equation directly. Is the right hand side, the non-homogeneous term, once the leading coefficient is 1. You see it? 1 times x double prime. Therefore, here we have capital F of t, the non-homogeneous term. So is 0 and t, x2 t is derivative 1, downstairs x1 e to the t times t, x2 t, derivative of the first times the second plus the first derivative of the second, and here we have a 1 derivative of t. So integral of upstairs main diagonal 0, secondary diagonal with opposite sign minus t squared, downstairs main diagonal t e to the t, secondary diagonal with opposite sign minus t squared e to the t minus t squared minus t e to the t, sorry, t e to the t, differential of t. So simplify, and then t squared and t squared disappear, also the negative sign, so it's just the integral of e to the negative t. Okay, so far so good. I know it's a very long problem, I'm aware of that, so but bear with me, we are really close. So the integral of e to the negative t differential of t is minus e to the negative t plus a given constant, see? On the other hand, u2 equals an integral of, now we are solving for the second mysterious function u2, and therefore we switch the second column in the Cramer system. x1 prime 0 f, and here the Wronskian. We don't have to repeat the term downstairs, we already did it for the first integral u1. So downstairs we know just minus t squared e to the t survives, so minus t squared e to the t. Upstairs it's going to be e to the t times t is derivative of the first times the second plus the first times derivative of the second, and then 0 and t. Upstairs in the numerator, secondary diagonal, luckily for us, is 0, so we just have t squared e to the t, downstairs minus t squared e to the t. Everything cancels except for the negative sign, so it's just the integral of negative 1 dt, right? And that is negative t plus d. So finally, the global solution would be u1 times t e to the t, the first homogeneous solution, plus u2 times t. So more specifically, u1, which was, here we have it, minus e to the negative t plus constant times t e to the negative t, plus u2 minus t plus d times t. Multiply this times this, the exponentials cancel, so it's just minus t, this times this, plus constant times t times exponential of t, this times this, minus t squared, and this times this, plus dt. Now, since d is an unknown constant, it's a blind constant, these two terms get absorbed within just one constant, I'm going to keep using D, abusive notation. So we end up having constant times t e to the t plus constant times t, the homogeneous solutions, right, minus t squared. And unsurprisingly, we get the same solution as before, constant exponential times t plus constant times t minus t squared. Okay. So finally, we get it done. Thank you very much and see you in another video.